Thank you, Mr. Chairman. Thank you, everybody. And especially thank you for the organizer for inviting me. So I'm going to talk about some application of computational aeroacoustic computational methods to problem of industrial interest for us. In fact, in the program there is a little mistake. My affiliation is not at Ecole Centrale Lyon. You will see that, in fact, I had a lot of relation with them, so it's not a big problem. In fact, my main affiliation is at EDF, Electricité France, which is the main electricity company in France. But I am also working for my research objective in INSIA, which is a joint research lab between EDF, CNRS, which is the main research governmental agency in France, CEA, which is the nuclear research, French nuclear research agency, and also ENSTA, which is a engineering school and a research institute. So our main industrial concerns are quite different to the main research concern of most of the people in the room. In this picture you see the main machine room nuclear power plant. And the beginning of our researches started with problem in main components that are present in the second loop of a nuclear power plant. You know that you are in a PW pressurized water reactor. You have a first loop with pressurized water and a second loop mainly with steam till the turbine. So on this loop you have many flow devices that are made of cavity or that disturb the flow. And we will see that many flow acoustic phenomena can develop in such devices and create many problems. So in such situation, we have to deal with turbulent flows, with compressible flow, shocks, because downstream of powered valve, the flow is transonic with very non-stationary and so very sensitive to coupling with acoustic resonances. So yeah, one of our main concern is the coupling between the acoustics and the flow. Of course, we have to deal with complex geometries and also with acoustic propagation. Not only in the pipe, but also, for example, outdoor propagation, because when we have some machines making noise, the neighbors are not very happy. So we have also to deal with studies about the noise in the environment. So we have started studying aeroacoustic quite a long time ago. At the beginning, we started with hybrid methods. So this kind of method which separate the aeroacoustic study into two steps. The first step dealing with the flow, so very often a CFD computation, and the second step dealing with propagation, with the definition, usually the definition of a source term. So we have developed at the beginning lighted analogy with runs computations at the first step. We have also developed lighting analogy with unsteady flow calculations, Urans or large eddy simulations. And as the lighting analogy involves mostly a green function to be solved easily, it was not the best for our situations, which deals mainly with internal flows. So we developed linearized Euler equation solvers, and we propose to use for the definition of the source term a stochastic approach we call SNGR. When you have to deal with the resolution, when you have to solve a linear Euler equation or Navier-Stokes, we have to deal with numerical methods. So we have used different methods as Mark 1, Mark 2, and fourth orders, because we wanted to go to the high order. We used also the kind of method like TVD, Artanier. And then when Professor Tam proposed the DRP scheme, we, of course, we wanted to use this kind of schemes. At this time, we thought that it was not in the scope of our mission to develop numerical scheme, I mean for a research department in an industrial company. So we saw that it was mainly the task of the academic researchers. So we decided to support the work developed at Ecole Centrale Lyon, and we support the PhD thesis of Christophe Boger, and then the PhD thesis of Olivier Marden. After that, we thought that we were able to develop, with all these results and this experience, to develop our own tool. And mainly during the PhD thesis of Thomas Emmert, we developed a numerical tool called Code Safari in order to be able to deal with our problem. So as you can see, we made a lot of work with Ecole Centrale, Lyon, because for the spatial discretization, we use the optimal central finite difference scheme they have developed on the base of the DRP scheme. For the time integration, we use the Runge-Kutta schemes developed also at Ecole Centrale by Berlin during his thesis. Same for the selective filtering. For the LOS strategy, we follow also the approach developed at Ecole Centrale, mainly based on what they call relaxation filtering, and which, in fact, this approach doesn't use any subgrid scale model. As I said, we have to deal with compressible flow and shocked flow, so we added shock capturing strategies. We use the Kim-Henley approach, which is this approach, in fact, add an hyperbolic viscosity, kind of hyperbolic viscosity, in order to capture the shocks. The approach of Boger and Bailly is more filtering strategy without any hyperbolic characteristic inside. So I think that now all these features are quite classic in the area of aeroacoustics. But we wanted to be able to test at least configuration of industrial interest. So we decided to use an overset grid or overlapping grid approach with high order interpolation between the grids, the kind of approach proposed by Univ in 2001. For that, we decided to use the free library Overture developed at Lawrence Livermore Laboratory by Bill and Shaw, because in our research division, most of the codes, scientific codes, simulation codes, use non-structured grids, so we didn't have any framework for multi-domain, for structured multi-domain or chimera approach. So we decided to use this software in order not to have to develop the framework of the chimera and the overlapping techniques. So one key point in this approach is to the communication between the grids through interpolation points. So the interpolation process is made on a transform grid. So it's quite well described in the Scott and Scherer paper. Especially, for example, the definition of what is called the delta, the offset. It's a key point in order to have accurate computations of the interpolations. So it's well developed in the Scott and Scherer paper. And of course, we use MPI in order to parallelize the code and to be able to have HPC capabilities. So now I'm going to present you some application we have carried out in the last 10 years, more or less. For example, the problem of the ducted cavity cavity. In fact, it comes from a real industrial problem. We had because some vibrations and noise appeared on a line, on a steam line, and in fact measurements on site led us to think it was due to a problem linked to this gate valve. So a gate valve, in fact, is an isolation valve. So most of the time it's open, and the gate is up in the top position, and when there is problems on the power plant, we can close and stop the flow. So most of the time it's open, and then you have the flow so the flow which is flowing on the cavity, and we know that when there is a flow on the cavity, so we have the development of shear layer. We have this feedback loop between the downstream corner to the upstream corner, triggering modes, hydrodynamic modes in the shear layer. So you can have, for example, two vortices in the shear layer is the second mode. But in our case, the cavity is in a duct. So the problem is that a strong whistling phenomena occurs when the hydrodynamic cavity mode and the acoustic duct mode match. So we decided to make some computation, we decided to make some experiment and also some computation on a simplified configurations. So you see the numerical parameters, and here we have an overview of the composite grids. So, on the top figure, we have a view on the vorticity in the cavity. So the Mach of 0.18 is the Mach is the Mach where on site we had the stronger phenomena. That's why we study a lot this Mach number. And in the bottom figure, we see the acoustic pressure in the duct. Acoustic pressure in the duct, and we see that that's the first transverse mode. So this result was already, even simple, were already an information, because our colleagues of the mechanical structure, they have found that the main mechanical modes, main vibration was a shell mode, and that only a transverse acoustic loading could be coupled with this shell mode. So this calculation was a proof that it was this phenomena linked with the cavity, which were the source of our problems. But we can compare also with the experimental we made. So you have the Mach number. Here we have the frequency. So there was the frequency in the cavity, at the bottom of the cavity. We have the frequency, and here the pressure level. So here we have what RM is Rossiter mode. That's the evolution of the hydrodynamic modes in the shear layer. And here we have the duct mode. So we can see that at for example, for the second Rossiter mode, here we can see very clearly the phenomenon of locking, because when we approach 0.18, use in black is the calculation, and in the empty triangle is the experiment. So we see that here the fluctuations are not the frequency of the fluctuation are leaving the Rossiter evolution to be locked in the first transverse mode. Here we have another lock-in, and here we have another lock-in. Here it's a spurious result. We don't know why. If we have a look on the pressure level, we can see that at 0.18 we have the main amplitude. So the calculation retrieve more or less this amplitude, not exactly at 0.18, a little later, and the peak is broader. But for example, we retrieve this locking between the third mode with the first Rossiter mode with the first duct mode. We retrieve it here. So despite some discrepancies, most of physical phenomena have been retried by our calculations. Another case, which is completely different. In the first case, for the gate valve, it was a constant pressure flow. Here, it's a case dealing with the high pressure valve, especially when the aperture is very low, and when the pressure ratio is very high. We use this test case of a planar duct between two reservoirs at a high pressure and a low pressure, and we we are looking at the phenomena with respect to the flow ratio. Why we have used this test case? Because it's quite typical of what happened downstream high pressure valve, but also because there is the experiment data of Anderson. So they made a lot of measurement on this flow, on this configuration, and mainly a lot of interferometry visualization. So when the downstream pressure is very low, we have a flow which is mainly supersonic. When the downstream pressure is high, we have in fact a transonic jet in a confined configuration, and we have very interesting configuration in the middle, because here we have very unstable situation where normal shocks forms into the duct, and this configuration is very unstable. So here again, that's the kind of grid we built. We use the grid, the downstream reservoir is computed because we want to have the right boundary condition at the end of the duct. So here we obtain here are the two configuration, the supersonic one and the transonic one. So I have some. So the first, okay. So here the calculation. So we try to have a correct grid at the walls in order to be able to capture the shear layers. So you can see several classical results. For example, after each shock refraction, the shear layer thicken. You can see also that it's also a well-known result. We have a double shock at the refraction, at the first refraction on the shear layer. And so if you remember the experimental visualization, it's quite close. Now for the intermediate situation, we capture this phenomena, which was first measured by Anderson. In fact, we have a shock, a normal shock formed in the duct, and this unsteady movement, in fact, is coupled with the longitudinal acoustic mode in the duct. So, in this situation, the pressure fluctuations are very, very high. So, in fact, on an industrial point of view, we don't want to have such a situation, especially if there is also, a mechanical mode, a structure mode close to this kind of frequency. Because in this case, any structure, non-structure can resist to such a phenomenon. So it happens once, and we broke a main steam line. Just on a historical point of view, we first compute this case in '93, So it was only with Euler solver, a TVD-R10 Euler solver, with only 50,000 points. And in 2007, we used Navier-Stokes in 3D with 20 million points. So, for example, here we obtain only stationary results. In the Anderson paper, it's very well analyzed. In fact, you have all these unstationary phenomena because you have communication between this cavity, the corner pressure, through the boundary layer. Because the boundary layer is not subsonic, and you can have communication, pressure wave coming upstream through this corner and making some destabilization. So the Navier-Stokes approach was needed in order to retrieve this kind of result, this kind of situation. We were also, during a moment, interested by rotor-stator interactions in the steam turbine. So, in fact, we found this classical test case in the aeroacoustic community in order to try to make some calculation in this approaching case. So here are the kind of mesh the grid we built. So here we have the velocity field, and here the pressure field till the far field. So that's it illustrates also the capability of the overset grid, because you can have fine grid around the bodies and then more coarser grid for the far field propagation. So I'm not going to talk about all these results. We have here the mean result and the turbulence result. So the results are quite good. There are some discrepancies, but also Mark Jacob, we made the experiment, told me that there were some problems in the experiment, so some of these discrepancies can be explained. In the far field, we retried the far field pressure spectrum, but the results are not very good in the low frequency range. I don't know if it's just because we didn't have a signal long enough to compute accurately the spectrum, or if there is another problem. But we decided to make a parametric study about the length separating the road and the airfoil. So here are some snapshots of the modulus of the spine-wise vorticities. We can highlight a shear mode where the shear layers reattach on the airfoil, and the flow in fact develops around a body made of the road airfoil as a unique body. For large spacing, we are in a wake mode, where the airfoil in fact is in the wake of the cylinder. If we have a look to the drag coefficient between on the road and the airfoil, we can see that the transition occurs between 3 and 3.5, the transition between the two modes. So, for example, the drag of the airfoil is always negative due to the presence of the road. Yeah. So here are some acoustic results. So we can see that there are the two gap value of 3.5 and 6.5 are the two configurations which produce the highest noise level in the far field. And in the wake mode, adding the airfoils make the flow noisier than for cylinder alone, and it's the contrary in the shear mode. Now another configuration, which is quite different because it was made during a collaboration between EDF and PSA Peugeot Citroën, which is one of the two main car manufacturers in France. So as the car engine are less and less noisy, in fact some aerodynamic noise have to be studied and treated. It's the case for the side view mirror because it creates some pressure fluctuation on the side window of the car, and it's really quite a direct way of transmission of the noise inside the car. So at PSA they made some experiment of a side view mirror on a plate, and so we decided to compute this configuration. So it was really a 3D complex configuration. So PSA had a CAD file, so the Overture preprocessor is able to read the CAD file, but it was not an easy task. So we needed 23 grids around the side view mirror body, and then we immersed this grid in the boxes grid for the modeling the whole domain. So another view of the shape of the volume grid, and here an image of the volume grid. So just a view of the flow developing downstream the side view mirror, and the grids downstream are made more coarser and coarser. So we see that effect. Here is an image of the swirl contour around the side view mirror. So here it's a slide about the experimental measurement, and the grid of the microphone on the plate just downstream the side view mirror. So when we compare, so it's a view of the pressure fluctuation field on the plate behind the side view mirror. So we can see what is called the pseudo-sound fluctuation convected downstream, but we can see also the sound radiated by away from the turbulent domain. So we obtain some good comparison in some places, and in other points much more unhappy comparison. So we here again it was in the low frequency range. So in fact, what was the main objective for PSA Peugeot Citroën? In fact, they wanted to be able to separate the contribution of the convective fluctuation and the acoustic fluctuation present on the side window to the noise radiated in the interior, because especially for the acoustic fluctuation, it was not easy to calculate. If you don't have really high fidelity simulation, it's not easy to calculate this contribution. And it's also not easy on experimental point of view. It's very difficult. You need to have a very fine microphone grid in order to be able to to separate the convective peak and the acoustic peak. So it's not easy at all. So that was, we carried out this calculation, because it's difficult on an experimental point of view, but with classic CFD is also very difficult, because in fact we destroy the acoustics, and it's very difficult to capture the acoustic peak. So in fact, all the data, the computed data on the plate downstream the side view mirror were computed by PSR with a lot of signal processing, and they obtained these KX, KY pictures for different frequencies, where you can visualize the convective line, the convective fluctuations, and you can see the acoustic circle on the around around the 0.00. Of course, as you go further on the high frequency domain, the separation is easier, and also you can see that the convective amplitude, the amplitude of the convective fluctuations is decreasing. So making the acoustic spot, the acoustic circle, more evident and more easier to detect. So in fact, based on this result, as you can separate the two sources of fluctuation, pseudo sound and sound, you can apply for each kind of fluctuation the right vibroacoustic methods, the adapted vibroacoustic method, and here you can see the level, the noise level in the car. In fact, yes, in the car. We imagine it's in the car. Due to the sound in red, and due to the sound, the acoustic fluctuation in blue. So now I'm talking about two new developments we are carrying out. So first, we are going to compute a new case. So I'm going just to show you, in fact, experimental results. We are just starting the building the grid. So experimental result obtained in collaboration with Professor Samir Ziada from McMaster University in Canada. In fact, it's a generalization of the cavity problem I showed at the beginning. But now the situation is a little more complex, because now we have a round duct, cylindrical duct, connected to a square cavity. So now the shear layer is a cylindrical shear layer connected to the different modes that can appear in the cavity. These modes here have been calculated with classical finite element acoustic software. And in McMaster, they have measured the noise in this cavity in different, pressure sensors, 3 here and 1 here. So with this position, we are able to identify every mode that develops in this cavity. So here we have the frequency, here the mean velocity, and the noise, the pressure, sound pressure level is indicated with the color scale. So we can here again we can see the lock-in phenomena between the shear layer and the acoustic mode in the cavity. So in this case, it's just more complex. but we can see that when the lock-in phenomena occurs, the amplitude is much, the amplitude becomes higher, become higher. And so I just talked about this new study, but we have also new developments. So because, in fact, our industrial needs are evolving, because since the Fukushima accident, more and more studies are concentrated on the safety problem. Most of the study related to the nuclear power plant I talked about were related to the second loop, where we have steam flow, which can be which can consider like a monophasic fluid. But on the first loop, which is a loop, as I said, dealing with pressurized, high pressure water, in fact, when we have problems, very often we have vaporization. And so, in this kind of problem, we have to deal with transient in two-phase flow, with shock wave, contact discontinuity, as usual, but also vaporization wave. So it becomes much more complex. And also, we have a problem in this kind of, when we have to deal with the volume fraction or the mass fraction, we would like to have to preserve the positivity of such variables. So, in fact, we started to make some study with a very simple two-phase model, just with the RLS system associated to some transportation equation for species. But in this case, we decided to develop in the same framework of a multi-domain. We decided to develop a high-order hyperbolic method based on the work of Nonomura et al. So, in fact, it's a mix of of a finite difference approach with Weno interpolation at the cell frontier. So in this case, when you have to deal with upwind method, you have to write, even if you are in a finite difference framework, you have to write your equation, your scheme as a finite volume, one. In order to apply then at the cell frontier boundary, the Weno interpolation and the Riemann solver, and so on and so on. So we just apply that to a classical case. It's in fact it's a shock wave going through an helium bubble in air. It's quite a classic test case, and when we compare, we can see the high level, the high resolution, the high fidelity brought by the high level, high order methods. If you have a look to other this case with second order method, you don't see the instability on the boundary of the helium bubble. Okay, so we have developed an high order numerical tool for CA, but also we want to extend, because we want the tool to be quite flexible, and because our problem are changing. And so we have current validation mainly for unsteady compressible flow and for acoustic interaction. Other capabilities are available, like moving grids, linear frequency solver, and also complex impedance for outdoor acoustic propagation. Our main objective is to have an expertise tool in order to be able to help analyzing industrial problems when we have problems, and it occurs. So all this work have been obtained with the collaboration of people of EDF, with also Sébastien Candel from Ecole Centrale Lyon, all the people of Ecole Centrale Paris, sorry, all the people of Ecole Centrale Lyon, François Vaner from PSA Peugeot Citroën, Bill and Shaw from Lawrence Environment Laboratory, and Samir Ziada from McMaster University.
Thank you for your attention.